Okay, welcome friends. We'll go ahead and start with a review. These are the subject topics we'll be covering. If we don't get finished, I can just go ahead and link older reviews for those subjects on our YouTube channel. Okay, but we're dealing with second order differential equations and later on Laplace transforms. Let's get started with second order homogeneous equations with constant coefficients. Just a quick review of the cases. So let me get my tablet set up, and I think we are good to go. Okay, so second order different constant coefficients. All right, so we know that we are dealing with a differential equation, a second order differential equation, where we have simply scalars, right? Numbers multiplying the derivatives of y and y itself. And it's homogeneous, so this is equal to 0. And we know that we try to find a solution in the form, we assume a solution in the form of an exponential, a simple exponential, where r is a constant. We differentiate this a couple times, stick it into the differential equation, and we find that in order to for this to be a solution indeed, we need this polynomial to be 0. So I'm not going to go through any of the derivations today because I know your exam is, I believe, on tomorrow, right? So, okay. We get the characteristic polynomial. And we solve for the roots by either factoring or using the quadratic formula. Okay, so, and there are three cases for a second order differential equation, and we have case number 1. The roots of your characteristic polynomial are real and distinct. So this is the real distinct case. And in that case, our solutions are going to look like, or our general solution to this homogeneous equation is just some linear combination of the fundamental solution set. Okay, so quick example. Okay, constant coefficients. And we know that you write down the corresponding characteristic equation. Here we can indeed factor. And we see that the fundamental solution set is E. So the roots are 3, and the second root is -2. Those are real roots and they're distinct. So this is going to be e to the first root times t, and the second function in our fundamental solution set is e to the -2t. Okay. And second, and of course, your general solution is just some linear combination of these two independent functions. And if we had initial conditions, I'm trying to save time, so we would then use them to figure out what the scalars in this linear combination are. Okay, so the second case is where the roots are real, but they're repeated. So it's a root of multiplicity 2. We'll just call that root r. So this is the real repeated root, or a root with multiplicity 2. Okay. Okay. In that case, we know that one of the functions in our fundamental solution set will just be our exponential raised to that root times t. And the second one, in order to guarantee linear independence, and we can use reduction of order to prove this. And also, let me turn off the audio notifications 1 second. All right, thank you. All right, would be, we would just multiply the first solution by t. It turns out to work. And that also guarantees that we have 2 linearly independent solutions. So an example, again, right, would be y double prime minus 8y prime. Okay, so we write down our characteristic equation, quadratic formula or factor. This, of course, is a perfect square for this case. So we have a root of 4 with multiplicity 2. Okay. So our general solution is just a linear combination of the fundamental solution set. So e to the 4t plus a multiple of e to the 4t, but multiplied by t for this case. Okay. And the third case, yes, thank you. So often, right, they'll just write this as a combination of the fundamental solution set for the general solution. Instead of A and B, they're used like C1 or C2 or something like that. So if that's what you're used to, for sure. Okay. All right. Third case is where the roots, we know that when you have a quadratic polynomial, it doesn't have to have real roots. It might have complex roots, in which case we have the roots are going to be necessarily complex conjugates. So you're going to have some complex root and its conjugate. So this is the case for complex conjugate roots. And again, no derivation, but our fundamental solution set is going to be an exponential raised to the power, which is the real part of your complex roots times t, or x, or whatever you want to use, and then sine of, and then you have the imaginary part times t. Okay, and the second function in our fundamental solution set is again an exponential where we use the real part, and the cousin to sine, of course, is cosine. So they always, if one goes somewhere, the other one is dragged along, it seems. Okay. Okay. So that's the third case. So as an example, very simple. You've seen this in physics with oscillatory motion and things like that. It's a homogeneous equation, constant coefficients. We can assume a solution of e to the RT. We can write down our characteristic equation. Oops, that's almost a mistake, right? Well, it is a mistake. There's no y prime, right? So the r would correspond to y prime when you're comparing the differential equation to your characteristic polynomial. So let me fix that, right? Y corresponds to r to the 0, if you will, so just a constant. All right, so we see very quickly that if you take the square root of -9, you're going to get plus or minus, square root of a negative number gives you an imaginary part. So, okay. So our general solution would be some combination, and what we would have e to the, and what's the real part? I'm sorry, what's the real part of our complex roots, right? So if we look at our roots, we can just assume that the real, well, I mean, it is, the real part is 0. Okay, so in our formula that we wrote down, alpha is 0, beta is 3. So our first solution is e to the alpha times t, sine of 3t, the imaginary part is 3, plus a multiple of the other one. Okay. Awesome. All right, and final example before we move on. I just want to make sure everybody's clear on these cases. Constant coefficients, homogeneous, so we're going to go ahead and write down the corresponding characteristic equation. And I guess I'll use quadratic formula. So r is negative of b squared. And this is 40 and 12 is 52. 32, 36. So square root of negative 36. Okay. So that's I times 6, since we're taking the square root of a negative number, and we see that our roots are complex conjugates. So our fundamental solution set would be e to the real part is 2 times t. We have a sine of imaginary part, 3t. Our second solution is, again, the exponential plus time cosine. Okay, very good. All right. All right, so that was, I guess, a necessary prelude to undetermined coefficients. So that is our next topic if you're ready to go on, if you feel comfortable with all these three cases. Okay. All right. All right. So the method of undetermined coefficients, not underdetermined, undetermined. Right. Okay. So what is this used for? Well, it's used for, number one, a second order, well, a differential equation that has constant coefficients. So here A, B, and C are not functions, but rather just numbers. So constant coefficients. Okay. And it's not homogeneous. On the other side, we have some function. And this method is used to find a particular solution. Oh, I should say something about GFT. GFT, so this is a, GFT has to be of a very restricted form. So GFT, let's write this in words, has to be a polynomial. Okay. Times some combination of sine and cosine, some linear combination, I should say. Okay. And in fact, these are all kind of simple. Like, so sine would be like a sine of AT. It wouldn't be something like sine of t squared, right? So it's just this linear combination of, I should just fix that right now. Okay, and finally, you can also multiply by a simple exponential. Something of the form e to the at, right? So again, no t squares, just a simple, the argument of this exponential is just a multiple of t. Okay, all right, and then you can use this method of undetermined coefficients. So I guess that's like third point, restricted to what the right-hand side could be. And in that case, we can use method of undetermined coefficients to find a particular solution. All right. To that original non-homogeneous equation. All right, so the steps for this would be to find the fundamental solution set. I'm not sure why I'm capitalizing this. Okay. So that is to say, you're finding the two linearly independent solutions to the homogeneous equation. Okay. Number two, we're going to determine the form that our particular solution takes. So determine the form of the particular solution. Okay. And does anybody does anybody want to remind us, or if you want in chat, you can say how, not how, but rather what two considerations do we use? Do we base the form of our particular solution? Okay. So it's going to be number one. It's going to be based on, well, okay, number one, we're going to assume that the particular solution takes on the form of the general form of the right-hand side, or a generic form. I'm not sure how to say that. General or generic, but we also have to look at, it's also based on the fundamental solution set. y1 and y2, right? You can also restate that as saying it's the nature of the roots of the characteristic polynomial, same thing. Okay. And we're going to go maybe through just some examples. But then once you assume the form your particular solution takes, you have to differentiate the particular solution in its general form. You substitute into the original non-homogeneous equation. And then get a system, solve a system of equations, linear equations. To find the to determine the coefficients. Okay. So this third part, of course, is just an exercise, a very tedious exercise in differentiating using product rule, using triple product rule, whatever, substituting and then solving a linear system of equations. Unfortunately, that's just the nature of the beast. But the fun part, of course, is determining. I mean, I think you get a lot of credit from your graders just if you know the correct form of the particular solution. So let's look at some examples. Well, actually, I should write down the form it takes, right? Okay. So I'm just going to quickly say the particular solution can be written as some power of the independent variable times the general or generic form of the right-hand side. Okay. Okay. So this part is based, well, as it states, it's based on the right-hand side function. So that's all you have to look at. This is based on comparing the fundamental solution set or the roots of your characteristic equation with the right-hand side function. Okay, and you want S to be the smallest natural number integer power, so a positive integer, of course. Sorry, positive integer power that guarantees that all the terms in your particular solution, all of them, are different or more technically linearly independent than everything in your fundamental solution set. That word every is important. Is different or independent. I'll just say linearly independent. Okay, so now we can quickly run through some setup, or sorry, some examples. YP prime and YP double prime? Alex, I don't understand the question. Maybe I lost the context. Well, we'll figure it out. Okay. So we're just going to run through some scenarios. Right. Okay. So this is constant coefficients. And the right-hand side is of an acceptable form. It's just a polynomial. Okay. So we're going to assume that our particular solution first of all is just general or generic form of the right-hand side function. So that looks like a second order polynomial to me. So we're going to write the most general kind of thing for a second order polynomial. So you see A, B, and C are undetermined as of yet. Okay, but then we might have to multiply by some integer power, smallest integer power of t, to guarantee independence. But to determine what S should be, we look at the fundamental solution set, or the roots of the characteristic equation equivalently. So characteristic equation factors nicely. So we see our fundamental solution set to the homogeneous equation is y1, and then we have that other exponential. All right, so we see that if our particular solution is just this, we are good to go, right? Because none of these polynomial-like terms is can't be combined with anything in the fundamental solution set. So S would be 0. Smallest non-negative integer then. Precision. Okay. Okay, so that would be the form. If the right-hand side, on the other hand, were t plus 3 and an exponential, like e to the 4t, I think I have. Okay. Again, our particular solution takes on the general form of the right-hand side, and this is a polynomial of degree 1 times our exponential, and then we multiply by some non-negative integer power of t. Okay, and we determine what that is by comparing all the terms, right? So if we didn't have this factor, we would get e to the t, e to the 4t, right? And would all these terms, both of them, be linearly independent from everything in the solution set? Okay, yeah. These are different I mean, they're all exponential functions, but because the powers are different, right? These are going to be considered linearly independent. You can check with using a Vronskin. All right. So that's it. That would be our particular form of the particular solution S is 0. Okay. However, if we have something like the right-hand side looks like one of our solutions from the fundamental solution set, like this, for example, we would assume our particular solution looks like a first-degree polynomial. Okay, and we know this is probably not right, because if I want to distribute and we see that even though the first term, it's an exponential that looks like something in our fundamental solution set. However, it's being multiplied by t, so that term is considered linearly independent from everything in the solution set, fundamental solution set. However, just because the first term is linearly independent from everything in the fundamental solution set, this is not. So we do have to multiply by at least t to the power 1. Okay, and if we did that, we would get t squared and t. Oops. Right. So this time, both terms are like one of these exponentials, but they're being multiplied by some power of t, and so these are going to be now linearly independent. So that's going to be the form of our particular solution. Oh, you know what? I should have just done this one to save time. Yeah, let's just say some second degree polynomial. But is that what I meant? No, that's not what I meant. Okay. So let's just move on to the next example. All right, so if we have, let's say, okay, so that's some constant coefficient second order differential equation, and then we have the right hand side, and it can take some forms like e to the t. Okay, and we look at the we try to find the solutions to the homogeneous version of this equation by writing down the characteristic polynomial, and I guess the roots would be we have a negative underneath the square root, so it's going to be 6i. Okay, so we know that our fundamental solution set, because we have complex conjugates for our roots, we have e to the real part of our root times t, and a sine of imaginary part times t. Okay, so all right, so let's figure out the form of our particular solution. We look at the right hand side. It's of an acceptable form for undetermined coefficients, because it's just a simple exponential and a simple sine. So we say that our particular solution is gonna look like the right-hand side function, but at any time you have a sine or a cosine, you got to drag along its cousin. So we're gonna have some generally, right, a combination of sine and cosine. So you include both sine and cosine, even if you just see just one of those on the right-hand side. And so would every term in our particular solution be linearly independent from everything in this fundamental solution set? Absolutely, right? Okay, these are different, not only are these different sines and cosines, right? That's 3t, this is 4t. They're also different exponentials. So there would be no need to multiply by some power of t. This would be it. This is, okay. This would be the form that our particular solution takes. And then we differentiate. Good luck. Plug in, and I'm sure we'll do an example, but all right. All right, so what would happen if the right-hand side some of the terms don't, well, let's just write it down. Because we need to move on, so I'll skip a couple examples. So this is the ultimate nightmare. I hope you don't see it. Okay. So we already know the fundamental solution set. It's the same characteristic polynomial as above. Okay. So our particular solution, well, the right-hand side, to me looks like a second degree polynomial. So I'll rewrite that in general. We have, well, yeah, this is a little redundant, so sine and cosine. How do I explain this? Okay, I'll just write it down. Then we have our cosine. So we're going to need a combination of sine and cosine. And then times our exponential. Okay. However, we might have to multiply by some power of t. So can you determine what s is here? Right. If you were to, oh, right, if you were to multiply everything out, right, let's say excluding this t to the s. If you were to multiply everything out, would every term be different or linearly independent from the fundamental solutions, from everything in the fundamental solution set? Mm. Oh, I see what you're. On example 4. Okay, well, you would have to anticipate here that, if you multiply this out, and by the way, I should just say it, we can assume that like a is 1, right? That's because if you distribute and you get like a times d, a times e, that's just a new constant. So here I would just probably say do something like that. But no, not all the terms would be different. If you multiply this out, you would get something, some multiple of like b, right, and then sine of 3t e to the 4t. And you would get some, I should say bc, and you would get eventually, if you multiply this with the exponential, right? So indeed, these two terms match the stuff in the fundamental solution set. So you would have to multiply by a power of t. So you try t to the power 1. And if you do that, then you would get a t in front of here. And so now all the terms would be linearly independent from everything. Okay, so here S would be 1, if you will. Okay, and we're doing okay on time. And one last thing. Switch to X for some reason. All right, the fundamental solution set here. Looks like we have a repeated root. So our fundamental solution set would be e to the 3t and then for repeated roots, remember, you have to multiply the first y1 by t to guarantee independence. And I should be using, of course, x. Gosh. Okay, so we have the general form of the right-hand side. So that is a first-degree polynomial times our exponential. And then we have x to some power. Okay, and for illustration's sake here, we would distribute, we're going to check all the terms, how they compare with the fundamental solution set. Okay. So looking at this term, we see that it looks like y1 in the fundamental solution set. Oops, wait a minute. Oh my gosh. I apologize, I missed writing a 3 over here. Right, so we look at that term and we see that it matches one of these guys, right? So we know that S has to be at least 1. Okay, and if S were 1, then we would get ax squared e to the 3x plus bx e to the 3x. But there's a problem, right? Because then this term is still can be still linearly dependent on something in the fundamental solution set. You'd have to then try multiplying by, or letting s be 2, the next bigger integer. And in that case, this would look like ax cubed. Right, and only now, finally, both terms in the particular solution would be linearly independent from everything in the fundamental solution set. So we know that we could stop, and we kind of have to. If you were to assume a larger value for s, you might make an error, or I'm not sure if you will be wrong or it just might be wrong, but it doesn't matter. So that would be okay. Do you guys actually want to go through the process of? Did you actually want to go through the process of determining coefficients? Or are you okay with that? Well, maybe I can start. Maybe I can say some things. All right. So here's an example: finding a general solution. Okay. So we know from our previous example that the fundamental solution set is e to the, let's just use x, okay, 3x. And we have a repeated root, so the second solution was x times e to the 3x. We know our solution is going to take the form of a second degree polynomial times that exponential. And by what power of x do we have to, we might not have to multiply to guarantee that all the terms are different, right? So we would have to multiply by, it looks like x isn't good enough, right? If we had just x, that would, when we distribute, we would get cx. So that would match that. So it looks like x squared is the better thing, and in that case, indeed, now all the terms would be different. Okay, perfect. So we've determined, we have the form of our particular. Why is t? Yeah. Well, no, I'm saying that this is not a problem, right? Because we let s be 1, and now if you were to multiply everything out, t times sine times our exponential would be independent from just sine or cosine and times the exponential. So this is not a problem. It's the solution to our problem. So yeah, I should have been clear there. Okay. Right. Right. And then you would have to differentiate a couple times and plug into the original. All right, the non-homogeneous version. And I guess the only thing, if you haven't already discovered this, I would say about a polynomial times an exponential. Right? When you differentiate, you use product rule, and so you would say you differentiate the exponential first. When you differentiate that, you just get a factor of a from the chain rule, I guess. So you would just end up multiplying that whole polynomial by that constant a, and then plus you would differentiate the polynomial while leaving the exponential alone, and you can factor the exponential. So it might be useful to do that, right? To know that ahead of time. Just product rule if you want to think about why that's true. All right. But you have to differentiate once. So I'm just going to say that's going to be, right, differentiate the exponential, you get a factor of 3. Okay, and then plus, and then you have the polynomial. Right, and then exponential just reproduces itself, so it'll be a common factor, so it's worth just factoring out, so that when you find the next derivative, I did something wrong. Oh, cubed. Okay, it's worth just doing some housekeeping there. before you move on to the next derivative. I know, this is, I do not enjoy it at all. Not at all. All right, so again, differentiating using product rule. If we were to differentiate the exponential first, we just get a factor of 3, multiplying our polynomial. And then plus just our polynomial again. Oh my gosh. You guys should have stopped me. I wasn't using my, I forgot. Okay. Forget all that. Remember, it's you have to add the derivative of the polynomial if you're using product rule. So, it's being recorded, by the way. Maybe you don't necessarily want to be trying to jot everything down. Just focus on the problem and at the end the solution and see if you can get there yourself. All right, so plus, and then now we have the derivative so of the polynomial. And that common factor, our exponential, we just take out. Tidy up and proceed to the next derivative. So I didn't really want to do this, right? And I'm probably not going to continue for time's sake, but I just wanted to show, and then you compute the second derivative, plug everything in, and you get a nasty system of equations. And I believe the particular solution is A turned out to be 1, B turned out to be 0, C turned out to be -1. Okay, so your particular solution will look like x squared and x squared minus 1, and then our exponential. So the general solution would be a combination of the fundamental solution set plus our particular solution. And at this point, if you had initial conditions, then you can use them to solve for A and B. Yeah, it's hard to do this during a review. I mean, when I put this video up, I'll just go ahead I'll just link to like older videos that we have if you want, of examples, if you want to practice undetermined coefficients. Okay. Oh, I forgot reduction of order. Okay, so reduction of order. Sorry, yes, I'm using A, B, and C, but often they'll just subscript their coefficients instead of using different letters. Now, we don't have enough undetermined coefficients to like go crazy. It's not necessary to go with the subscripts, but you can. Okay. So the next thing we're going to talk about is reduction of order. Right, so reduction of order is, what is it? Where is it? Right, okay. So that's when you have a second order differential equation where you know one of the solutions to the homogeneous you know one of the solutions to the homogeneous equation, and you can use it to reduce the order of the differential equation to that of a first order to get the second solution. Okay, so we're going to write this in its kind of conventional form. Notice the coefficient for y double prime is 1. So you might have to divide so that you get that conventional form. This time, p and q are not necessarily constants, but they're functions of the independent variable. And you're given one of the solutions. You can always confirm that we indeed have a solution. I think you were asked to do that on your homework or something. So this is given. And you want to get a second linearly independent solution to this homogeneous equation. And what we assume is that the second solution is just some function, and I don't know what you call it in your class, v or u or something. It's a function of the independent variable times y1. So that's a function. So we make a lot of assumptions in differential equations about what the answer looks like, and it turns out to be correct. So, and then if you derive the formulas, we'll get that this function has to look like this. It's an integral, and you're integrating e to the negative of the integral of p divided by the first solution squared. So you end up doing two integrals. So you integrate once to get that exponential, and then you integrate again to get u. So that's our formula for reduction of order. So it's important to write this in conventional form so you identify p, the function multiplying y prime, correctly. Right. Let's do an example. So this example is going to be from, if you're familiar with Euler equations, this is where this is coming from. So we have non-constant coefficients. It's homogeneous. Okay, and suppose we're given that one solution is simply, well, t squared. Well, hold on, yeah, t squared. Right. Then you want to find another solution, independent solution. Okay, so we assume that it looks like a function of t times t squared. And we have a formula, right? And, well, but before we go on to the formula, right, what has to happen first to this original differential equation? Yes, it's only a reduction of order is a way of finding a second function in your fundamental solution set. So by definition, fundamental solution set are the solutions to a homogeneous differential equation. So yes, reduction of order only works, yeah, for homogeneous. Is it homogeneous or homogeneous? Is there a difference to the two words? If anybody's, I need to figure that out. Okay. Homogeneous, homogeneous. I think it's just pronouncing it differently. Okay. All right. So we would have to first write this in standard form so that we correctly identify p, the function multiplying y prime, because here p is not equal to -3t, right? So divide everything by t squared. We're assuming t's, actually we're assuming t's positive, but okay, it doesn't have to be. It's definitely not 0 though. So divide everything by t squared. Oh yeah, thank you. It is two pronunciations. So I must have been spelling it incorrectly. So it's homogeneous or homogeneous, but I was using this thing, so crap. Well, that's embarrassing. Okay. So, okay. But now that we have it in standard form, we find the function multiplying y prime. We call that p in our formula. Okay. And it looks like, according to the yellow highlighted formula, we need to figure out the integral of p, or minus p dt first. So we get a log of t, and t is positive, so. Okay. So e to the minus of that result, e to that result would just give us t cubed at the end of the day. So the numerator there is t cubed. The denominator is simply the first function squared. So y1 squared in the denominator. Y1 is t, so it's t to the 4. So you get log of t. There you go. So y2 then we said is this function that we found according to our formula times t squared. So I'll write it as t squared times log t. And if you know Euler, Cauchy-Euler equations, they might have known that. The two negatives did cancel out. So I apologize. So we had a minus, so according to the formula, but p of t was negative 3 over t. So those did indeed cancel out. And there's nothing too tricky about this, right? Except, maybe the integration. As long as you remember to write something in standard form, identify p, and do your integrals right, you're good to go. So here's another example. This is not an Euler differential equation. I don't know, Jack, about whether you have to check for linear independence using the Wronskian. Wasn't the Wronskian on the last exam? I don't even know. No, it would be. I guess that would be technically this exam. But maybe they want you to use the Wronskian. So, yeah, I mean, I think in this example, yeah, we can do that. Okay. All right. So write it in standard form. That's boring. Okay. And we are given one of the solutions. You can confirm that it's a solution if you'd like. And we want to find their solution in the form of y1 times some function. Okay. So u must be e to the negative of the antiderivative of p divided by y1 squared. So I hope you're all like Olympic level integrators by now. Just do a little bit of algebra there. I guess properties of exponents and logs. Turns that into you don't get to take. Oh man, you have to memorize all those integrals. Oh geez. Okay, those cancel, and we get x squared times x to the -2. So that's 1. And 1 over sine, I believe, is called cosecant. So we get the antiderivative of cosecant squared, analogous to the antiderivative of secant squared, right, is tangent, because the derivative of tangent is secant squared up to a constant. The antiderivative of cosecant squared would be negative cotangent. There's that kind of weird skew symmetry going on with secant and tangent, and then cosecant and cotangent. Okay. So we get our antiderivative is negative cotangent. So y2 would be y1. Y1 was given as sine x over x times this u that we've just computed using formulas. And that simplifies to minus cosine x over x. All right. Cotangent is the reciprocal of tangent, so cosine over sine. Indeed. Okay. Now I can technically drop, right? So I can drop this negative, right? Why is that? Well, if you have a solution to the homogeneous to a homogeneous equation, then any multiple of that is also a solution. So it doesn't matter. That constant multiplying that what you get doesn't matter. So we can just assume, right, that our y2 is just proportional to what we get here. So I'm just going to keep it simple. Okay, that's our fundamental solution set using reduction of order, where the first solution was given. And if you'd like, you can check for independence. The Vronsky is a test of independence, again, without deriving it, which always disappoints me, but you know, you guys have an exam coming up. So it's going to be the determinant. And here you're going to get y1, y2, and then y prime 1, y prime 2. Determinant of this thing. What's the derivative of y1? So you get so you'd have to use product rule or quotient rule, whichever one you prefer, to deal with this sort of situation. Right, so this is a y1 prime. Right, y2. And y2 prime. I'm using product rule in my head, so. And we compute the determinant, and we all know this motion, this cross product looking. So that product minus minus, and then the other product, right? Minus that. Okay. Oh boy, joy. Okay. Okay. So we have some things that indeed cancel. We have two terms that are simply negatives of one another. And then we can factor out 1 over x squared, and we're left with sine squared plus cosine squared, which reduces using Pythagorean trig identity. And so we know that if the Vronsky is not 0 on some interval, then we say that our functions are linearly independent on that interval. So here, this is going to be not 0 for or on, right? Either of these integrals intervals. However, we would only use if we had an initial value, we would only use the interval where the y value or the x is in the correct interval, right? So if they had given y of 1 is 2 or something, you see that x is 1. So whatever solution we get at the end of the day, using our initial conditions, would only be valid on the interval containing the initial value for x. Right? So this is, we would get a solution that's valid just on the interval where the initial value of x is. If you had y of -1 or 2, right, then the solution would be valid on the other interval. Your solution doesn't extend past singularities, right? Okay. All right, so yes, indeed, these are independent. Yeah, and Vronsky will be used in variation of parameters, exactly. Okay, cool. We might use this one again when we do variation of parameters. Yeah. All right, so variation of parameters. I think we're doing okay on time. All right, so variation parameters. So it's a method like method of undetermined coefficients in that it gives you a method of finding a particular solution to a non-homogeneous equation. Okay. However, it is more general, right? For undetermined coefficients, you have to have constant coefficients, right? And the right-hand side is restricted to like polynomial times some simple exponential times some simple combination of simple sines and cosines. Okay. Okay, so let's review that method. So you have a second order differential equation written in some standard form, so the coefficient for y double prime is 1. And you have a right hand side, let's call it g of t. Okay. So to get just a general solution, right? No, so first find the fundamental solution set to the homogeneous version of this problem. This is a necessary step even if they just ask you for a particular solution, because the fundamental solution set is used in the formula for variation of parameters or formulas. Well, they might. So when do you use variation of parameters? And when do you use the method of undetermined coefficients? Well, here you have to have constant coefficients, for sure. And the right-hand side is restricted to polynomials, exponentials, and sines, cosines. Variation of parameters can be used when it's more general, when you don't necessarily have constant coefficients, and the right-hand side might be something like tangent, right? Tangent of t is not an acceptable form when using undetermined coefficients. Right? Or something weird like x times log x or something like that. And variation parameter, anytime undetermined coefficients can be used, variation parameters of parameters can be used, but not the converse, right? So there are some differential equations for which we can use variation of parameters, but to find a particular solution, but you wouldn't be able to use undetermined coefficients. So this is more general, if you will. And I took it a little while to list all the restrictions or conditions. Maybe that'll probably just tell you, I don't know. Okay, so we get our fundamental solution set. And then we're going to assume that our particular solution looks like, maybe I'll use C, a combination of the fundamental solution set. But here, C1 and C2 are functions of the independent variable. So very reminiscent of our assumption for reduction of order, where we assumed the second function in our fundamental solution set was some function times the first, right? That was for reduction of order. And then, right, so these are functions. And formulas that you will have to know are for what these coefficients turn out to be. So again, no derivation here. It's pretty much crunch time. So C1 would be the negative of the second solution. So you have to make sure you keep track of what you were considering y1 and y2 times the right-hand side divided by the Wronskian of your fundamental solution set. And C2 would be y1 times the right-hand side divided by the Wronskian. You anti-differentiate. So those are our two big formulas. And then your general solution to the original is going to look like, as always, a combination of the fundamental solution set plus the particular solution you found using variation of parameters. And I now mention this because, what did I mention that? Oh yeah, A and B, okay. At which point do you want to solve for A and B? Can you solve for A and B like here when you're looking at considering the homogeneous equation and you have the homogeneous part, right? Are you able to solve for A and B at this point, or do you have to wait till you find a particular solution? Right. So if you had initial conditions, right, and you want to for A and B, at which point do you do it? You do it after the part you find the particular solution. So don't try to figure out A and B here. Get the particular solution for. So we would and get the particular solution by applying the initial conditions only after you discover the particular solution. So apply the initial conditions at this point. Okay. All right. Let's get to it. Let's get to the example. So I'm going to reuse our previous problem. Okay, so we definitely cannot use undetermined coefficients here because the coefficients for the y and its derivatives are not constant. We have functions of x. But we should rewrite this in standard form before proceeding. So at this point, you would try to find the solutions to the homogeneous version. And so there, I mean, that would be easy enough to roll one problem into, to roll two problems into one if they give you one of the solutions here, right? But we already know the solutions are sine x over x, cosine x over x. So if you're just joining us or whatever, you weren't listening, we derived these solutions previously using reduction of order. Okay. Cool. So now we would assume that our particular solution is just some combination of y1 and y2, where the coefficients, right, are not just numbers, they're functions of x unknown to us. But thankfully we have formulas. Or I'm thinking I'm saying thankfully way too early because I don't know what these integrals would be. Okay. So what was the formula for C1? It's the negative of the second function in your fundamental solution set times the right-hand side divided by the Vronsky. So I would probably compute the Vronsky first. The Vronsky turned out to be negative 1 over x squared. We computed that somewhere on the previous page. Okay, so you computed the Vronsky. We can now apply a formula for C1. Negative of y2, where's y2? Cosine. G is the right-hand side, and the standard form of that equation okay, divided by the Vronsky. Well, that doesn't look like a good time to me. But you see that you're expected to know integration by parts, apparently. Negative? What do you mean we can get a negative? Oh, why is the negative? Let me highlight it. Is this your question, like where this negative is coming from? No, y2 is not negative. I chose it to be positive. Yes, indeed. Yeah. Yes, so over here we found y2 to be negative cosine x over x. But we said that if you have a solution to homogeneous equation, then any multiple of that is any constant multiple of that is also a solution. So just to keep things like nice, I just decided to scale by right -1. So technically I should be saying that this is proportional to that. So we just decided to multiply that by -1. Okay. You could have kept a negative in there if you want. It would have not changed the process. Okay. All right. Cool. So now we have to, oh my gosh, integration by parts. So polynomial times trig or exponential, I would just use integration by tabular integration by parts. So we have the polynomial, which we're going to differentiate. I'm going to put that in the differentiate column, I don't, whatever way you've learned to organize that. And you start differentiating until you get 0. And then you have the integration column, so that's going to be the cosine. And you start anti-differentiating until you reach the row with a 0 in it. Anti-differentiate, anti-differentiate, anti-differentiate. For integration by parts. Cool. So now we're just gonna, we know that we follow this pattern where you go product that corresponds to u times v. Then we have a minus as part of the formula. And then the product corresponding to the next use of integration by parts. And then we alternate signs to get plus. And then this product. Yeah, the alternating thing comes from the integration by parts formula, of course. Right, where if you don't get a simple enough integral in the integration by parts formula, you might have to use integration by parts again, and so you'd have minus and then a negative coming from the integration by parts formula when you use it a second time, so it'd be the plus. Okay. Ike. So cool. We get 3x squared sine minus a negative, right? Minus part of the formula, but we have a negative product. And then plus, and then negative 6 sine. Oops. Yuck, man. All right. All right, so in C2, okay. So y1, where's y1? Okay. G is the right-hand side in the standard form, and the Bronskin we've computed. Cool. Wow. Now that well, okay, we're good. So you'd use integration by parts again. Tabular method, preferably. Okay, so great. We have C1 and C2. Geez, all we have to do now is multiply with y1 and y2. All right. So c1 gets multiplied by y1. And then plus, and then c2 gets multiplied by cosine x over x. So crapola. So, but you know, if we combine these terms, right, you can use Pythagorean trig identity just to get 3x. The middle guys cancel, they add to 0, and then finally we get, in combining those, factoring out a negative 6x, we get sine squared plus cosine squared is 1. So our particular solution at the end of the day reduces to this. So now we can write the general solution. Okay, which we said was combination of the fundamental solution set together with the particular solution. So cool. Now I could have, oh my gosh, I don't have the solution to this. That's okay. So we're good. I think that's enough variation of parameters. Do you have any outstanding questions for tomorrow about the variation of parameters? All right. I mean, it's just knowing the formulas, right? Standard form, make sure you start with that. And then the integration. All I can say is good luck. Okay. All right. So what is the next? Yeah. So what did your professors say about Euler equations? As in, like, in terms of what's going to be on the exam? Because I didn't see them on the practice exam. That's why I was kind of like leaving it to the end. Uh, Okay. Did they say anything specific about Euler? It wasn't mentioned. Right. Well, since it's not on the practice exam, what I'm going to do is just probably link videos to it that we created already for Euler. I could just go over the cases if I can recall what they are. Okay. Right. Yeah, maybe I can quickly mention them. Right, so an Euler equation is just going to be it's nearly constant coefficient business, except you don't have constant coefficients. The y double prime gets multiplied by an x squared. The y prime gets multiplied by an x. Without going through the formality of y is what I'm trying to recall what this is. I think you assume that This is a change of independent variable. So you assume that x is like e to the t. And just compute your derivatives. Well, e to, yeah. Okay. All right, with the deriving, let's assume that y for the time being is just some power of t. That's like the form that your solution takes. Okay. Or sorry, x. No, I'll use t. All right. And if you differentiate once, twice, with respect to the independent variable there, you plug it in. What you've done there is simply change the non-constant coefficients to a case of constant coefficients. So a times t squared y double prime. B times t and then y prime. And then y. Okay. And here we're going to assume that t is positive, even though you could do it for negative, as long as t is not 0, right? Okay. So you're going to get t to the power r when you do the algebra, and you can factor out a t to the r. Okay, and so if this is to be 0 for all values of t, it's this thing that has to be 0. And so that's the characteristic equation for an Euler equation. You set that equal to 0. So characteristic equation for Euler. Anytime I start writing Laplace or Euler, it also starts off cursive for some weird reason. Okay. Right, so then you'd want to find the roots of this polynomial. You can rearrange if you wish. And get the solutions. Okay. Right. So then there's the three cases as before. So if to this characteristic equation you get distinct real roots, that's the easy case. Right, then your solutions look like this. y1 is t to the r1, and y2 is t to the r2. That's simple. Okay. In the case of real but repeated root, so let's just call that r. The videos are on peer tutor. We have videos on peer tutoring YouTube channel. So you can just search peer tutoring YouTube, and using the YouTube search function, you can look up 2420. There's like weekly reviews and past exam reviews and so on. I'll link to it when I post this video in case. All right. All right. So the problem there is, of course, you get one of your solutions is t to the r, but the second solution has to be linearly independent, like t to the r times something, but you wouldn't multiply it by t, you would multiply it by the natural log of t. Okay. And that really has to come from the background to this, where we're actually replacing the independent variable x, which we consider positive here, with e to the t. And if you go through those motions, if you can watch one of the videos if you really care to see how that's derived, this log of t. Maybe you can try variation of parameters if you wish. Or sorry, reduction of order, I should say. And the third case was your roots are complex conjugates. So in those cases, your solutions would look like, right. Well, what were the cases for, what were the solutions for just a constant coefficient thing that was like x? Sorry, I'm confused. E to the alpha x cosine or sine beta x. Y2 was, so now this is just for my say, it's like a thought bubble. I'll erase it. Okay, but if we okay, so that becomes e to the alpha x becomes, or sorry, e to the x alpha just becomes t to the alpha. Okay, beautiful. And then what does x become? Well, I should say e to the t equals x. Yeah, that was the right one. Or is it e to the x equals t? Yeah, I think that's right. So that would be x is log t. So you're going to get sine of beta. Okay, there you go. Log of t. I know it looks weird. Okay, now you can ignore all this. Y2 would be to the alpha and cosine beta log t. So that's rough, but okay. So, you know, make up your own, right? I mean, you have a template, so just choose some numbers. For A, B, and C, and see what happens. And let Wolfram Alpha or somebody check you if you get the right solution. Okay. So I didn't have anything prepared for this, but choose your own adventure here. Okay. All right. Let's see. Oh, okay. So that was just a quick overview. Again, I don't know. It's not on the practice exam. I don't know. You can ask your professors. All right. So the next topic then is going to be Laplace transforms and step functions. So you're not solving differential equations with Laplace transforms on this exam, I believe. You're just practicing finding Laplace transforms and finding the inverse Laplace transforms and rewriting a function, a piecewise function, as a single expression using step functions. So let's go over that. All right, so let's just look at the step function. Okay, let's just get down to the business. So the idea is if we have a piecewise function, let's just make something up. Yeah, that's good enough. So I should say 0 for t is less than 0. Okay. Okay. So this is a piecewise function, and you can rewrite it as a single expression using step functions. So a step function, it can be written like, it's written like this. Sometimes it's written like this. Okay. And all it is like a permanent on switch before time c. That's this number or that number. The step function is just 0. Okay. But at time c, it gets flipped on. So in our binary world, that's just 1, and then stays on. So it's like a permanent on switch. This goes, oops, and just becomes 1. And this means exactly the same thing. It's just a step function that turns on at 0 translated to the right by c. Okay. And we can use it to rewrite a piecewise function as a single expression. And the way we do it is we simply say that, okay, right at this time, so t is just there. I mean, you can say that it's just a step function that turns on at 0. And then you introduce this t. But then at time 1, you turn on your permanent on switch. And what you want to do is introduce the corresponding piece of your piecewise function, but then subtract the already existing piece that's already been, like, it's there because this is already turned on at time 1. Okay. Then plus, we have a step function that turns on at 3. And you first introduce the new term that you want, but you take away the preceding term. Right? So that would be, right, so a kind of in general, right, if you have some g and h for your piecewise function, right, and this is, let's call it g1, g2, and so on, just to see the pattern. You just first just write that first piece down as long as it's just valid for positive values of t. Okay, and plus, and then you have a step function that turns on at this time, c1. And you always just say that it's the piece you want to introduce, and then you subtract the piece that you want to extroduce, so to speak, that was on previously. And then you keep doing this for all the endpoints of your time intervals. So now we want to introduce G3, but we got to get rid of the preceding term G2. So G3 minus G2. So that's the general pattern. You could keep going if you'd like. Okay. And we want to be able to do this because, well, right, we want to solve a differential equation with the right-hand side as a piecewise function, and we can take advantage of Laplace transforms because there are formulas for transforming step function times function. All right. So maybe we can continue with that example. How would we find the Laplace transform? So we want to find the Laplace transform of f of t. So for this, we're going to need a table. We need a formula. So let me just write it out. Okay, formula. So we need a formula for the Laplace transform of a step function turning on at time c times a function of t. So the way I would do this is just think of the step function when being transformed becomes a decaying exponential. Right? Okay. And then times the Laplace transform of this function of t, but you replace t with t plus c. Okay, so the order of this, and you can derive this using the very definition of Laplace transform. Function times this decaying exponential, t dt gives you a function of s. But you can derive that yourself. But the order, the way you can quickly conceptualize it, I guess, step function becomes an exponential, a decaying exponential, so minus. So these kind of go together. And then to finish the Laplace transform, just replace t with, at each place you see t, replace it with t plus c, plus. It's important, plus, okay, in f of t. So that's what this kind of means. You first evaluate the function at t plus c, and then take the Laplace transform of the result. All right, so as an example, which I, yeah, okay. Oh, that's a bad example. That's not what I meant to do. Okay, so let's do a quick example of you really got to keep it simple. This might have been on your exam review. 1 second. So just t squared or something. Okay. So you have a step function that turns on at 3. And this is your f of t, right? So according to the formula, the step function will become a decaying exponential function of s, right? Your differential equation starts in the t domain. After the Laplace transform, you get something in the s domain. Turns out that you don't need that you can just use algebra concepts to find a solution in the s domain and then return that solution back to the time domain. Okay, but neither here or there. So times Laplace, and here we're going to take our function and replace all instances of t with t plus c. Don't make sign mistakes here, so use parentheses, plenty of parentheses if necessary. Let's tidy this up. We get e to the negative 6, e to the negative 2t. And then here we just, on the exam review problems, you had a cubed, so you would have to expand that. But here it's just squared, so we get 60 plus 9. Right. So now we know that Laplace transforms are linear. I mean, they're an integral, and integration is linear, so we can just factor out the constants. And we're just now left with taking the Laplace transform of an exponential function times a polynomial. And I guess you would use your table to then recall the formula, right? What's the Laplace transform of e to the at times a function of t? Gosh, it's just the Laplace transform of g of t evaluated when t is equal to, oh, sorry, not t. So you get a function of s, right? And so then you just evaluate this at s minus a. Oh my gosh. I gotta check. I don't want to tell you wrong. 1 second. I have a table somewhere. There you go. S minus, yeah, that's right. Yeah. Yeah, so you just evaluate this at s minus a. So it's like a shift. This is also sometimes written as if the Laplace transform of g we call f of s, right? And this Laplace transform evaluated at s minus c would look like f at s minus c. So sometimes you might see this formula written as the Laplace transform of g, but evaluated at s minus a. But here the order is just find the Laplace transform of your function. You get a function of s. And then replace the s's with s minus a. Shift. All right, so with that interlude over, I guess, tables. Let's keep going. We have this business already. Okay, and then this we just kind of ignore. I mean, not ignore, but it's going to be causing a shift. And we compute instead the Laplace transform of this polynomial. Okay, but after we do so, we cannot forget to replace s with s minus c, c being, what is, or a, I guess, a being -2. Yeah. Okay. So then you go to your table, and you know the Laplace transforms of polynomials, or t to some power. We know that's n plus 1 factorial divided by s to the power n. Okay, so the Laplace transform of t squared. Okay, let me just double check all these. When I, it's from memory, so I'd just rather. Oh crap! I'm glad I checked. We didn't write that down. Okay. Right, it's going to be n factorial divided by s to the power n plus 1. Ouch. Okay. That's a bad. That would have been a real bad. Okay. So t squared, that becomes 2 factorial divided by s cubed. Then you have 6. Leave the constant alone. Then Laplace transform of t is 1 factorial divided by s squared. And so by this rule, right, if you have a constant, just think of it as like a t to the 0, you can still use this rule. You get 0 factorial, which is 1, divided by s to the 0 plus 1. So you just get the Laplace transform of a constant is just the constant divided by s. Okay. However, this is bad notation, right? Because I have to evaluate this at c minus a being -2. So maybe I can suggest instead, right, I mean, if you're comfortable with this, that's great, but maybe you can say on the side, consider consider this Laplace transform, right? You get your answer. That's f of s. But we want to evaluate that at not s, but s plus 2. in this case, right? So that just means replace all instances of S with S plus 2. Yeah. And you're expected to be able to go the reverse direction as well. Cool. So that's it. That would be our Laplace transform. So yeah, I don't know. It's a lot of material for it. Okay. So what else? Uh, did you change the S in the exponential? Yep. It's not a problem. I'll just look through our peer tutoring channel for older stuff if you wish. I'm still probably going to do some inverse Laplace business here. Okay. Uh, just right. So okay. All right. So I'm going to do another example, and just to see how to deal with this business. Oh, that's an S, not a 3. I have to write my S's this way because otherwise they look like 5s to me. Okay, so here, again, we have a differential equation in the time domain, or sorry, t domain, and then we find the Laplace transform of the whole business to get something in the S domain. And you should be able to, they expect you to use the tables in order to go the other way. Given it's some function in the S domain, you want to see what the corresponding function is in the t domain. So that's inverse Laplace. Notice there's 2 reasons you would know that's inverse, because they use the inverse notation, and furthermore, this is a function of S. So we're in the S domain, we want to go the other way. Okay. Stephen. Let me just answer the question for Stephen there. All right. So the example I was giving was the Laplace transform as a step function times f of t. So I was doing this. Okay. And so we used the rule for finding the Laplace transform of step function, right, times something else. And the rule was that you can think of it, right, as the step function becoming this exponential. So e to the minus cs, right? So the Laplace transform of e to the 5t, sorry, 5 would be e to the negative 5s, and so on and so forth. Okay. But then times the Laplace transform of a new function, right? Well, it's the old one, but we replace t with t plus c. So the Laplace transform of step function that turns on at 5 times t cubed or something. The step function corresponds to a decaying exponential here, negative 5s. And then we multiply by the Laplace transform, but instead of t cubed, we replace t with t plus c, so t plus 5, and then we cube that. Okay. So we expand and then find the Laplace transform. Where I get to the near the end when you changed from that to that, but now where it changed? What? Hmm. Um, hmm. I guess because we use two different rules, maybe we're conflating them, right? Because there's the rule for finding the Laplace transform of step function times something, and then there's the rule for finding the Laplace transform of an exponential in the time domain times some function. So that's a different rule, right? So there's the shift rule, and I'm sorry, the step function rule, and then there's the exponential times function rule. Two different rules. This was just the Laplace transform of f of t, and you get a function of s, so you're going to just replace each s with s minus a. So there's two different rules. Maybe that's why it looks confusing. You changed the constant powers. I changed the constant powers. I did? Oh. Oh, yeah, okay. Yeah, no big deal. Yeah, I wrote 3 instead of 6 by, I exchanged the powers. Right, right. Thank you for catching that. Those silly mistakes. There you go. Thank you for that. All right. So we should be able to find, okay, to continue, all right, we're looking at inverse Laplace. So we're going to have a function of s. And so then you have to use the table in reverse. Maybe I can take a quick snapshot of what do I need to use? Alrighty. All right. Cool. Good reference there. Okay. So we're just using the table in reverse where, on the left column you have a function of t, and in the right column you have the corresponding function of s. So we're going from the s column, right, to the t column, if you will. Okay. But you have this exponential in the s domain, so there's a rule, and it's exactly this guy, right? Or if you'd like, I would rather think of it this way. Right, so this rule, so when you see that exponential in the s domain, you know that's going to correspond to a step function in the t domain. So let's write down the rule that we're going to use. And it is the following: e to the, Laplace transform of minus cs times a function of s. Okay, the other way. What am I trying to say? Okay. I'm trying to say the right thing. Okay, the inverse Laplace. Right, so this is going to turn it into a step function in the time domain. Okay, and this we're just going to find the inverse Laplace of, but then replace t with right, t minus c. Right. So you're going to get f of t minus c, where f of t is just the inverse Laplace of f of s. So let's just put that into practice. Right, so going from the time domain, if you recall, to the S domain, step function turned into a decaying exponential, and then we found the Laplace transform of f of t. But then we replaced s with, we replaced t with t plus c, and then found the Laplace transform. Here, kind of going doing the opposite as we're going in reverse, right? We would the exponential becomes a step function, and we find the Laplace transform of big F to get a function in the time domain, but then we replace all t's with t minus c this time, and going the other direction. Okay, so let's put that into that formula into practice. So we're finding the Laplace, inverse Laplace. All right, so the exponential turns into a step function that turns on at pi. Right. So then, following my own advice, I'm just going to consider the Laplace transform, inverse Laplace transform of this business. So if you're going to use the table, does anything look like it might work here? Right. So we have s plus 1 squared plus 2 squared. So it looks like it's like somewhere in here. That's not a good color to use. So this is as probably complicated as I don't know. It's a whole new concept, right? Second order differential equations and all of a sudden Laplace transforms. Kind of wish they had that kept that partition right, on the exam, but that's okay. Right. So to use these formulas, you got to match them up. So every once in a while, so you'll have to introduce terms and factors to make things work. Okay. So matching these up, we see that A would be like -1. And since 4 can be written as 2 squared, we see that B would be 2. Right. So what we have is actually neither one of these. If you want to use equation 20 there, or row 20 of our table, you would introduce S minus A. Well, so you need to see S minus the -1. You need to see S plus 1 in the numerator. So of course the the common trick is just to add that in, and then at the same time subtract it out. And then you would split this into 2 separate terms. And inverse Laplace is also linear, so you can just find the inverse Laplace term by term. So let's see, what about the second term? In the second term, notice that there's a b in the numerator, so b is 2. So you need to introduce, right, so, but the second term would probably be using this rule. Right, this turns out to be e to the alpha t, e to the at, and then you get a cosine of bt, just from the table. If you wish, you can derive those. They're not too bad. Yeah. Oh, sine. My bad, sine. Right, but before you use this, the b that you have in the denominator must be what's in the numerator as well. So we're going to simply, since b is 2, we're going to simply introduce that factor by multiplying the top and bottom by 2. So those are the two kind of sleights of hand, algebraic hand that you need to make that table working, to introduce terms or introduce factors by adding or subtracting or multiplying the top and bottom by the same thing. And yeah, we find the inverse Laplace is linear. So according to the table, this becomes e to the, what is a? A is negative. No, sorry, that should be a minus 2. Right, so since a is -1, the formula says that we should get e to the at, so e to the negative t. Okay, then we get cosine of bt minus a half, and then the inverse Laplace of that guy we saw is e to the negative t, and then sine of 2t. Cool. Okay, awesome. Right, so we found the inverse Laplace of just this animal right there. Okay. All right, so we can write it down. However, according to our rule, we have to replace all instances of t. Oops. All instances of t with, what is it? T minus c, right? So in our problem, c was equal to pa. Right? So we replace all instances of t with t minus pi. You can simplify that if you wish, but I don't wish to, so, right? I mean, yeah, this one's actually kind of easy, but. All right, beautiful. So that would, right, an example of finding inverse Laplace using some rules in this that can be found on the table, introducing terms that you need to make formulas match to the table. All right. And I guess just notice on the practice exam, there's a partial fractions business thing. So so maybe you're expected to, there's a problem, something like this. I have this on the piece of paper, so I'm gonna go soon. So I'm just gonna, let's see, 5, I guess 5. So you get, oops, it should be S domain, of course. Now it's U7. So another tool, right, that we can use is, well, things in the S domain tend to look like rational functions, polynomial over polynomial, possibly times some exponentials. So we know when you have these rational functions, we can sometimes rewrite that function more simply as a bunch of simple fractions, simple rational functions. And so you have to know how to use partial fraction decomposition. Okay. So for such a problem, remember that well, first of all, we have an exponential. Okay. Also, we have a constant of -1. We can just bring that outside. That exponential in the time domain just becomes, that's supposed to be minus as well, right? What does that exponential become? What's the Laplace transform of e to the 7s? Does anybody know? It's like, probably been better if that was a -7, to be honest. Yeah. So we're just going to consider that a -7. Right. So we can use our rule for Laplace transform of step function there. It's just easier to let. So if it's -7s, this would become a step function that turns on at t equals 7. Okay. And then, right, we're going to consider the Laplace transform of this rational function, the inverse Laplace. And so here, this is impossible, right? Unless you have software. And even the table, all right, this is too complicated. So you just assume you do partial fraction decomposition. So you have like a squared term, so that's going to be repeated linear factor. You have a single non-repeated factor, so that would be, and then this is an irreducible quadratic. So that would be, right, the quadratic is degree 2 on top. You tend to have 1 degree less, so some line, some linear factor ds plus e. And it turns out that I won't do this, but a is to b 0, c is -1, d is 1, and e is 0. If you want to practice partial fraction decomposition. And then we know that we can find the inverse Laplace term by term. This inverse Laplace is linear. S plus 1, what, whoa. Number 8. Oh, yes. Good catch. It's a +1. Ooh. All right, thank you. All right, and so then we just have to use the table in reverse. So this, what should this be? If you have a s squared in the denominator, right, what do we want to see in the numerator? Well, you want to see 1 factorial. We don't have one, but that's okay. Just take out the 2. And now, so the Laplace transform of this would match, this is 1 factorial, so t to the power 1. Okay, this guy looks like, well, the Laplace transform of a constant, but it's shifted over by 3, so it's probably going to be an exponential. So on your table, I believe there's a formula for that. If you don't, right? Yeah, it's really this one. more generally. But here n would be 0, so really we're looking at this one. Okay. You have 1 over s minus a. That turns directly to an exponential in the time domain. But if you have s minus a to some power, then you got to match it up to formula 23. So, okay. So that's just going to be an exponential at 3t. And then this guy looks like, what does that look like? Sine or cosine? Looks like cosine. Yeah, right there. Too easy, yeah. Anyway, tables, you gotta know how to use them. Yeah. So yeah, I just wanted to mention that partial fractions might be involved in, again, manipulating so formulas match to the table. Anyway, I'm going to take off, and you guys enjoy your evening studying or not. Good luck on the exam. Check out our YouTube channel, peer tutoring. If you have, maybe you can find a video that works for you. All right, later.